All right, in this video, we're going to start to see how we can start to bring sine, cosine, and tangent into the situation. All right, in the previous video, we saw that when we created reference triangles, we were able to describe all of these angles regardless of their size, 130 degrees, 230 degrees. We could all describe them as a reference triangle in a certain quadrant, okay, or in a certain part of that grid. So because we started drawing right triangles, we can now start to talk about trig. So let's consider an angle theta in standard position drawn for you here, such that the terminal arm goes to the point 3, 4. First thing we're going to do is let's draw in our reference triangle. So the reference triangle, as always, is between the hypotenuse and the x-axis. So in this case, it's right there. All right, so do we know any side lengths in this triangle? Well, we actually do, because if you think about how to graph the point 3, 4, that, we would start at the origin, you'd go 3 this way, and then you go up 4. So 3 that direction, 4 in the up direction, gives us really the side lengths of a right triangle. So the x-coordinate of the point is that bottom side. Let me just zoom in here for a second. So that x point, or the x-coordinate here on the point on the terminal arm is kind of like the length of the bottom side, and this y-coordinate becomes the length of the vertical side. Now, to name the hypotenuse in this case, well, first of all, we know how to figure out what that is because we can use the Pythagorean theorem. So a squared plus b squared equals c squared. That's 9 plus 16 equals c squared. And you might recognize those set of numbers as being part of the 3, 4, 5 Pythagorean triplet. Should be an equal there. Okay, so we now know the hypotenuse is 5. So just as we called this bottom side the x side, because we kind of get it from the x, right? We can also call this height, okay, that side there, as the y-coordinate. We can imagine this, this terminal arm, if we were to spin it around the circle, or spin it around, we'd be creating this big circle that goes all the way around, and the radius of that circle would just be the length of that side. So the radius of this circle would be 5. So for that reason, we are now going to call this hypotenuse side, we can call it radius because we're imagining it as being part of a big circle. So we also have another set of names for these sides based on theta. Okay, opposite theta is the y side. Adjacent to theta down here is the x side, and the radius is our hypotenuse. So we have kind of a lot of names for really the same sides in this triangle. Okay, so let's go back to our notes. And we have the length of the sides. We've kind of given them several names. And down here in C, we say, now that we're done drawing the angles on this set of axes, on the xy axes, we can start to call this adjacent down here, we can start to just refer to it as, well, in this circumstance, it's always going to be that bottom x side. All right, the opposite, that's always going to be just that y side, or the y-coordinate of the point that it goes through. And the hypotenuse, we can always refer to that as r. All right, so how does that change? It's not absolutely essential that we kind of change things like the Pythagorean theorem, but if we wanted to, we can say from now on in this sort of grid situation with our triangles and angles in standard position, a squared plus b squared equals c squared. Well, that would become, if you think about it here, it would be like x squared plus y squared over r squared. Okay, so we can just sort of repurpose the Pythagorean theorem and put in the a side, the b side squared, and the hypotenuse is r squared. Okay? Now, can we still think of it as a squared plus b squared plus c squared, where c is the hypotenuse? Sure, it's the same thing. It's just that c is r the hypotenuse, the b side is like the y height, and a is like the bottom side, x squared. Okay? So just a different way of putting the relationship. And in the same way, we can sort of redefine our trig ratios. Cos of theta, which is normally a over h, we can now start to call, well, the adjacent side is like the x side, and the hypotenuse is the r side. So we can say, well, that's just the x side over the hypotenuse. Similarly, sine theta, which is opposite over hypotenuse, is equal to, well, what's the opposite side? Well, that's the y coordinate, and h is the r side. So that would be the y side over the hypotenuse. And finally, tan theta is equal to opposite over adjacent. The opposite side is y, and the adjacent side is x, and then we have that kind of connection as well. So what we're doing is we're taking the Pythagorean theorem and the trig ratios and kind of like using x, y, and r, we can kind of redefine the Pythagorean theorem and the trig ratios using those letters. Okay? Might be, it's also actually good to note here that for tan, when we're finding y over x, if we think back to grade 10, we actually did that last year when we went the y side or opposite. That's kind of like how much the line is rising, and the adjacent side is how much it's running. So y over x is kind of like saying rise over run. So yet another set of names we can kind of give these sides as rise and run for going up and going sideways. So if we take a look at tan, well, this is really just rise over run. So for that reason, tan is slope. Okay, that's a very helpful thing to understand about tan. Okay, so let's give the three angles or the three trig ratios for this particular trig function. Well, according to what we got here, we've got cosine of our angle is adjacent side, which is 3 over the hypotenuse, or the radius, which is 5. Sine of the angle is 4 over 5, and tan of the angle is the rise over the run, the y over the x, or the opposite over the adjacent, all the same thing, 4 over 3. Okay, so kind of just a lot of things written down there, which is basic, but let's just not forget that this is basically just trigonometry with a triangle and the Pythagorean theorem. We're just giving new names to everything and making connections to the grid. Okay, on the next page, we've got another example. So here it says, the terminal arm of A in standard position goes through a point, -5, 12. Give the exact value of the three trig ratios for A. Okay, so let's move out of the first quadrant so that we have an angle that goes through the point -5, 12. Well, -5, 12 might be, say, about there. Okay. Now, if I draw my thingy like that, my terminal arm, and then there's my initial arm there. Okay, here's the angle. This time it's called A instead of theta. Well, we can now drop down our side that makes a reference triangle. And in that reference triangle, this little thing here we're going to call AR for the the reference angle. All right, we also know some side lengths to this thing. We know that, I'm just going to check my colors here on the previous page, see if I can keep it the same. Okay, I got it. All right. Hey. We also know that here, the bottom side is kind of like how far we have to go to the left. So that's -5. So we are going to allow the side lengths of the bottom, like the x and the y side, we're going to allow those to be positive or negative when needed. Okay, so since we're going 5 to the left, we're going to call that -5, and we notice that's also, right, it's that x coordinate. Likewise, we've got the y coordinate giving us how much we have to go up, giving us that this side here is 12. So the only thing we got to figure out now is what the hypotenuse is. So we're going to use our Pythagorean theorem. A squared, or x squared, plus b squared, or y squared, equals c squared, or r squared. Okay, the fact that the side was negative here doesn't really matter, because when you square it, we get 25. Then 12 times 12 is 144, equals r squared, so that's 169. All right, when we square root, we have to remember that this could be positive or negative square root of 169. So we'd seen in previous videos in the first or second chapter that whenever you use square root to solve an equation, you have to acknowledge that your answer that you get on the number side could be positive or negative. So the r is either positive or negative 13. But since r represents the radius of a circle going around, we're going to say r is always positive. Okay? It's always the length of that line, and we're going to say the length of that terminal arm is always going to be positive. So in this case, r is just 13, positive 13. Okay? So let's put that up there on the diagram. All right, so now that we have our three sides of our triangle, we can give the exact value of the three trig ratios for A. So cosine of A. Now, even though A is this big angle here that opens, into the second quadrant, we can still use the reference triangle to get the numbers to make our cosine ratio. So cosine of A is equal to adjacent over hypotenuse, or the adjacent side is the x side, so -5. And the hypotenuse is r, so that's 13. So all I'm doing is I'm looking at the triangle and I'm really just going adjacent, opposite, hypotenuse, and filling in the blanks. Sine is opposite over hypotenuse, or x or y over r, so that's 12 on 13. And tan is opposite over adjacent, or y over x, so 12 over -5. Okay? Now, I'm just going to write that negative in front and call it -12 over 5. So notice what we got here. We have some numbers, some fractions. Some of them are positive and some of them are negative. And we've seen this before. We saw that when we did the cos of 50 and 130, and we did it on the big calculator on the screen a while back, sometimes the number came out positive and sometimes the number came out negative. Well, you can see that since the x side, the yellow side, is negative, any trig function that uses that side, that's going to affect the sign. Okay? So this kind of begins to explain why some of the trig functions are positive in places and sometimes they're negative in places. Okay? All right. Let's take one more example. And this time, we're going to be in the third quadrant. going through the point -8, -4. Now I'm going to approximately put that here. It doesn't matter that it's kind of exactly to scale. -8, -4 is a point approximately there. So we're talking about this big angle, and it's called B. Okay, we know we can still find what the sine of B, the cos of B, and the tan of B are. We can still find them, but what we have to do first of all is we have to draw on our reference triangle so we have some numbers to kind of work with. Okay, so our reference triangle is right between the terminal arm and the x-axis. This little fella in here is called BR. That's our reference angle. Okay, we can use the coordinates of the points. Since the x coordinate's -8, that tells us that this side is 8 to the left, so we're going to label it -8. We've got this, the y coordinate's -4, so that's how much we have to go down. So we can say -4 is that side. And let's do Pythagorean theorem. -4 squared plus -8 squared equals c squared or r squared or whatever you want to call it. So that's 16 plus 64 is equal to r squared, which is 80. Now I know when I square root both sides, I got to go plus or minus, because that's a rule in math that you should use that the plus and minus sort of square root principle. But I know that r is always going to be positive, so I can just go r is equal to square root of 80, and I know it's going to be just positive because r always has to be positive. Okay, one thing here is let's see how can we simplify square root of 80. Okay, square root of 80, I'm going to break that up into 8 times 10. I'm going to break this up into 2 times 2 times 2, and 10 breaks up into 2 times 5. So the square root of 80 is this equivalent to the square root of 2 times 2 times 2 times 2 times 5. Well, I'm not sure if you did it this way or not, but one way that we can simplify a square root is anytime we have two things being squared, if we square root them, it's just going to be one of them. So the square root of 2 times 2, which would be 4, is just 2. The square root of this 2 times 2 is just 2. So every time you have a pair of numbers, you can kind of take them out, and the square root of that, the two numbers, is just going to be one of them. So here we end up with 2 times 2 is 4 root 5. So r is equal to 4 root 5, positive. 4 root 5, always positive. Okay, so what does our cos become? Well, cos is adjacent over hypotenuse, or we can think of it as the x side over the r side. Okay, all good. No matter how you slice it, it's going to be -8 over 4 root 5. And we can cancel factors. So we can reduce this to -2 over root 5. Now I know the bottom can be rationalized, as you guys did last year, but we'll just leave it there for now, at -2 over root 5. Sine B is opposite over hypotenuse, or y over r. But whatever you want to call it, it's still -4 over 4 root 5. And we can reduce the 4's and write this as -1 over root 5. Tan B is opposite over adjacent, or y over x, or rise over run. Again, whatever you call it, it's -4 over -8. Okay? So that then reduces to the negatives cancel, and that reduces to 1/2. Okay, so those are the 3 trig ratios for that angle in standard position. And one last thing that we can do is, if we did want to rationalize these, remember this fraction here, to rationalize the bottom, we need to multiply it by root 5. So rationalized, okay, I'd be okay with just leaving like that for now. But eventually we want to get to rationalizing the denominator, so that's negative 2 root 5. And on the bottom, root 5 times root 5 is just 5. Okay? Because root 25 is what that would give you, which is 5. Likewise, this one can multiply top and bottom by root 5, leaving us to negative root 5 over 5. Again, these are the same answers as before, but they're just the rationalized version of them. So again, this or this means the same thing. This or this. And the last one, 1/2, we're kind of done there. Okay. So the last kind of topic we're going to look at is, what is the deal with those kind of the sign things, and why things positive in some places and negative in the other. So we're going to take a break and do this in the next video.